Before we leave, I would like to take 5 minutes to make a live demo, show you how all the material we have seen is implemented in practice. I will make the demo in Danske Bank's production systems. This is a new development for us, and its implementation is experimental for now, but we can still give you a good idea of how everything fits together in a practical risk calculation engine. The training set is computed with our front office pricing and risk management system with the same model and the same parameters that we use for live pricing. The system is coded in C++ and runs on parallel CPU. When the training set is ready, including the pathwise differentials, the system communicates it to the training platform developed on TensorFlow and running on GPU. The platform trains the neural network, which means that it finds the connection weights that minimize the combined MEC, as we have seen in the presentation. After training is complete, it communicates the trained connection weights back to the front office system. The weights encode the pricing function, so the risk system can now predict prices and risks as functions of states by induction through the twin network. Armed with a learned pricing and risk function, the system can easily compute exposures, quantiles, and all kinds of risk aggregates. So this is Superfly, Danske Bank's proprietary pricing and risk management system. I'm piloting Superfly from Excel, but the action takes place on the quant server in the upper right corner. In the lower right corner, you see the TensorFlow trainer listening for training requests. First, I create a transaction by scripting its cash flows. This is a worst of 4 autocallable bond. If you are not familiar with cash flow scripting, think of it as a translation of a term sheet into a language that the system understands and interprets. I also explicitly smoothed the various barriers involved in the autocallable so that Superfly can safely differentiate the cash flows with AAD. Next, I load an appropriate model for the transaction. In this case, a set of local volatility models à la Dupire correlated with our official correlation metrics. The model is configured for live pricing and calibrated to current market data. I have everything I need now to price the transaction. You can see that the autocallable bond is worth around 96 today. I could also compute its AAD risk report, but I will skip that today. Instead, I'm going to decorate the script to learn a pricing function for the autocallable bond in 6 months on December 20. I am instructing the system to learn the pricing function of the autocall on that date, which authorizes me to use the learned approximation in the script to make arbitrary risk computations. Here, I'm simply storing the pathwise value predictions in the variable PV6M. Now, I enable training and recompute the value. What this does is instruct the system to compute a training set complete with pathwise differentials. Watch the TensorFlow listener in the lower right corner. When I fire the computation, it will pick up the training set and train the neural network. Doing it now. Superfly generates the training set and wakes up TensorFlow. TensorFlow trains the neural network and displays the learning curve for our reference. Then it communicates the trained weights back to Superfly. Armed with an encoding of a pricing function, the system simulates market scenarios and computes the future value of the bond in those scenarios. In this case, I have 8,000 market scenarios produced in the pricing model for simplicity, but it doesn't have to be the case. The market scenarios could be generated in arbitrary models, including ones calibrated to historical data. The system now computed the future value of the autocallable bond in the 8,000 market scenarios by evaluation of a trained neural network. I can pull these 8,000 values from memory, along with the final payoffs on the same 8,000 market paths. With these numbers, I can easily compute an exposure, a quantile, or an arbitrary risk aggregate. Here, I just display the distribution of a future value in red, along with the distribution of final payoffs in blue. Actually, I could script an arbitrary risk computation along with the cash flows of a transaction, including XVA, CCR, FRTB, or CMMVA. We have seen how we can learn and use a pricing function on one given exposure date. The machinery is easily extended to multiple exposure dates and for a limited additional cost. But this is a story for another day.